Hey guys, welcome back to the Beginner's Guide to Restoring Early Tube-Based Black and White Televisions. When we last left off, we had applied power to the set for the very first time, but just to the tube filaments. They all lit up, everything looks good, so we're taking it to the next level. We are going to gradually apply power to the full set, see what happens. I'm going to weave in a little bit schematic and theory along the way. Before I try powering it up, I thought it would be useful to draw an enlarged, simplified diagram of the power supply and explain potential problems. Let's start with 120 volts coming into the set. We have a power switch, and then it goes right to primary of the power transformers. No fuse in this, no thermistor, nothing. It's just 120 volts AC switched right to the primary. Other side of that, we have a number of windings. We're just going to simplify this and talk about the secondary winding and ignore the filament windings. Secondary is a center tap. Imagine you're coiling wire around a form, and then halfway down you take a loop and come out and then continue on. That's what they call the center tap. It's halfway through the coil. That comes out and goes to ground, right to the chassis. The other two sides go to our rectifier tube, the 5U4. They go right to the plates. Opposite that we have the cathodes. Like this. They connect directly together inside the tube, actually, and they go to our pi filter. So this is our 5U4 rectifier tube. It has two diodes in it, and these go to that pi filter I talked about earlier, which has a nice power choke, and then this is our rectified filter DC coming out. We have two electrolytic filter caps on there, big cans on the chassis, and that is grounded. At this point, if we didn't have this circuit here, we have rectified AC. It'll look like this. This is what you call a half-wave rectifier. Perhaps if I draw a diode symbol in here, it'll be a little more familiar to you. So this is how the equivalent circuit to diodes. Diodes, we call it the anode, and the bar, the line of the diode is a cathode, and the tube, it's plate and cathode. So plate and anode are the same, cathode, cathode. It may seem weird to think of the cathode as being negative. That's actually where the positive voltage comes out. The current flow is from the left to the right. Now, by adding this turns this ideally into this. And this is a big old iron core and that filter choke there. And these are the positive sides. So, potential pitfalls. Possibly there could be a short in the power transformer, meaning the enameled wire, it's wrapped on an iron core, that enameled coating could fail. This could have been overstressed because of problems in the set, overheated. We saw that wax dripping out. You could have a short over here. Really, I don't think I've ever found a bad power transformer in a TV. Not these early TVs, because they're so robust, over-engineered. They can take a lot of abuse. It's far more likely as we have problems over here. Potentially some circuit in the TV is shorted out and drawing excessive current that can blow open a winding inside the filter choke. Absolutely, I've seen that. A really common issue too is these capacitors. This should be a perfect insulator. That's why they draw it as this symbol. It should not be possible for current to get between these plates in the capacitor. Over time, the chemicals, the insulators inside the cap start degrading, and you start getting current flow coming down through here, which causes them to heat up internally and to not do their job. So you start getting ripple in the output. You'll hear that as hum in your speaker. You may see sound bars in your picture. That's a really common issue. That's why generally everybody shotguns replaces these electrolytics. We're going to try to form them up. Talk more about that later. If there's a problem in this where these are shorted out or something down here is shorted out, in addition to this potentially blowing open, it can also put tremendous strain on this tube, which can cause red plating, meaning there's so much current flowing through here that these are getting hot. There's more current flowing through than it's designed for, and it will start glowing red inside the tube. If something's really bad, like a dead short, when you turn it on, you could see sparks inside the tube and it will probably blow the filament apart. All those problems I have seen, all the problems on this side. Shorted caps, open filter chokes, blown open rectifier tubes. Absolutely, that's the common kind of problem you're likely to see. Hopefully we won't. Let's find out. Okay, put the chassis on its side. Voltmeter hooked up to this cap up here. It's just a single section electrolytic. We have a rectifier tube. It's our filter choke. 2 wires coming out. One goes to the tube and one goes to that cap, and there's an orange wire. This is the main B plus supply to the entire set. So I'm just going to hook this guy right on there. I'm going to turn the variac on. So output voltage now is actually 0. Let's go up a bit to around 35-40 volts. And current's pretty low. It's got a low filament voltage. Just everything's going to be lower filament voltage, lower plate voltage. But you can see the rectifier tube starting to conduct. We've got a whopping 1.5 volts, but keep going up. Current draw is slowly increasing too. So why is it slowly increasing? One, tubes are weakly warming up, or just barely warming up. Bigger factor is that those caps are starting to reform, even at this low voltage. So as they form up, they have less leakage current. They pull down the supply less, so the voltage goes up. Now, could I do this with the main chassis disconnected? Sort of. Running a power supply with no load, which is what the situation would be, it would just be power transformer, rectifier tube, filter choke, and a capacitor going to nothing. Problem with no load, one, it's not a realistic test. This thing was designed to have a certain load, and it's expecting that. Without it, the voltages are going to be higher than they would normally, and if I was to put the full AC line voltage, the voltage on the capacitor would exceed its rating most likely. I think it's rated for 450. It would likely go over 500 with no load on it. If I really wanted to test this on its own, I would have to put a resistive load on this orange wire to simulate the load of the main chassis. And not a good idea at all to run power supplies with no load unless they're designed for that type of operation. Alright, well, I've been babbling. It looks like we've settled it at about 4.5. So I'm going to ramp things up a little more. And, of course, that's going to go up. So I'm going to keep doing this. I'm going to keep an eye on that voltage. It should keep going up and up and up, while the current only modestly goes up. Current draw of the entire set. So B+, we're getting up there. We're up to 40 volts already. And our current draw is 0.6 amps or so. So you get the idea. Just keeps, every time this plateaus, turn up the variac a little bit. Plateau, turn it up a little more. Oh, whiteboard time again. This term, reforming capacitors, form it up. What the heck are we talking about? Well, let's go with a simple symbol for an electrolytic capacitor. What we have. Let's call this the cathode, the negative side, and for the positive side, we'll draw it like this. And that's going off to our power supply. This is going off to our set, and this is going, well, I'll draw a modern symbol. That's going to our rectifier. So this will be the output of our 5U4 or our 5Y3G. It's going to be DC with a bunch of ripple on it. This capacitor will help smooth that out. So with this capacitor in the circuit, instead of being like that, it might reduce it to something like that. Then we have a filter choke, then another filter cap, and by the time we're past that, so after this, actually, because we have a pi filter, we're going to have a nice choke, and then another one of these caps. And this is ground. So by the time you get out here, it's going to be darn near zero ripple. Okay, great. What's the issue with these caps? Just like everything else in these sets, parts are 70 plus years old. Things deteriorate. Inside of this capacitor, we have a jelly roll of aluminum, an insulating absorbent material. Well, think of like a paper towel in between the two layers of metal that's impregnated with a solution, an electrolyte. It's sort of like a classic lead acid car battery. Problem over time is that, well, there's a few things. It can dry out. If the seal is not perfect, it's a water-based electrolyte material, it can dry out. You may sometimes pick up an old can, you can actually hear it rattle, and it doesn't weigh very much, because all the electrolyte is the moisture is evaporated, and you're just left with, well, not much left inside. Or the chemicals start to break down. The exact chemicals are kind of a trade secret, so I don't know exactly what the chemical formula for it was. I know the really old ones used borax or boric acid, but by this era they were a little more complicated. At any rate, just like with a lead acid car battery, you have lead and you have, what is it, lead sulfate, lead oxide or something. There's an insulation layer that builds up on the surface of the metal from a reaction with the acid. It's the same with this, where that electrolyte helps chemically. The aluminum reacts with the electrolyte to build up a compound on the surface that can deteriorate. When we're talking about forming it up, we're trying to invigorate, reactivate that layer, that aluminum compound layer that helps the capacitor do its job. That happens by applying voltage to it. However, if we were to just put full-on voltage into this, let's say it's a 350 volt cap, and if we put a full 350 volts on this, and this is in bad shape, the chemicals have broken down, that insulating chemical layer has broken down, it's going to conduct. It's not going to be, an ideal capacitor was a metal plate, and no current shall pass. A perfect insulator. Over time, even if you buy new caps, if they have a shit on the shelf for a few years, they're going to have leakage current. That's what the term is, meaning current is going to flow where it should not flow, because this insulating layer in here is deteriorated. So the idea is, instead of putting a full 350, which will put potentially an excessive amount of current through this, which can cause internal heating, which can wreak havoc where this insulating layer can completely fail, the metal can short together, and violently, it can get hot inside, steam can build up, it blows the end of the cap out. We want to do it slowly. So instead of 350, maybe we put 50, and we monitor the current. Ideally, it'll be less than 1 milliamp when it's fully formed up. A new modern cap would be microamps. But for these old caps, I would say if you're under 1 milliamp for a main filter cap, you're doing okay. But if at 50 volts, say we get 5 milliamps, we're going to want to slow down for a bit. And if it's capable of reforming, and maybe it's at 5 milliamps at 50 volts, watch it. After a minute, maybe it's down to 4 milliamps. A little bit longer, down to 3. And maybe after 10-15 minutes, it's below 1 milliamp. Then you turn this voltage up, maybe go to 75 volts. The leakage current will go up again. And you wait. And ideally, the leakage current drops down. So every time the leakage current drops down and levels out, you turn up the knob a little bit on your Variac if you have one. Or if you're using a dim bulb tester, you go from a 60 watt bulb to a 75 watt bulb to a 100 watt bulb to a 125 to 150. Every 10-15 minutes, swap out the bulb. Or in a Variac, every 10-15 minutes, turn up the knob a little bit. Until ideally, we do get up to that 350, and we have less than 1 milliamp flowing through that cap. That's where we want to be. Now, it's also possible if this is dried out, you can get to 350 and have maybe 0 milliamps going through this. However, if you put a capacitance meter across it, it's going to show nothing. It's the opposite problem. One is that the chemical's there and it's broken down. The opposite problem is it's dried out and is no longer acts as a capacitor. It's like it's not even there. In which case you could tack in, at least temporarily, a new cap across this, which is an old service tech trick. When it's dried out and it's an open capacitor, rather than a leaky or shorted capacitor, you can tack temporarily a new one across it. I say temporarily because if you tack one in and it restores function to your device, great. You know what the problem is? You have to remove the old one eventually because it could short out. It could develop problems. You want it out of the circuit entirely. If you want to keep appearances, fine, leave it up there, but clip out the connections below. All right, so this is what we're going to be doing. We're going to be powering it up slowly while monitoring the current draw. Also, you can feel this, see if it gets warm, and check this voltage. I hope that makes sense. Okay, we are up to 80 volts AC going into the sub of the B plus at 235. Things have been holding steady. No sign of anything. No sound out of the speaker. I have the volume turned up all the way. And no light on the CRT. Let's keep going. 90 now is around where I might expect something to start happening. Let's go to 100. Now there is a fuse and a flyback, which I did not check. That could be blown. Oh, I'm stupid. Let me turn this off. Forgot to hook up the audio cable. Alright, let's resume. Maybe now we'll hear a little something out of the speaker. 100 volts AC going in, about 300 on the B plus. tubes a little bit. I thought I would at least hear a crackle. $110 going, and this should definitely be enough. Oh, hey. No hint of sound, but so as I was saying, I'm gonna turn it off. This is the reason to do this. We know the picture 2 has some life. We know the flyback's working. We know the horizontal oscillators are working. The vertical oscillator is working. The yoke is working. The power supply is doing something. It's awesome. It's awesome. No sound. Usually it's the opposite. Where this will be blank and you hear something out of the speaker. But the fact that this did something is fantastic. Because this is the best piece of test equipment you can have after your multimeter. Is the screen itself once you have something on it. Because of course, as things improve, we only had this much height. So we fix the vertical circuit. This should expand. If we feed a test pattern in, it may not lock, it may not look so good as we replace things, fix things. It should get it to be a better and better and better image. Likewise with the sound, we have no sound. Well, hopefully we can figure out why and get something, and then as we improve the sound circuit, it gets better and better and better. That's a fantastic start to this project. This seems like a good point to wrap things up. If you do find a set in very fine condition from the 40s, early 50s, and you decide to do a controlled power-up, this is about what you can expect if it's going to do anything at all. You're just not going to find something that old with original parts that's going to work. Remember earlier I talked about components deteriorating over time. In particular that the larger components deteriorate sooner simply because there's more material to deteriorate. The vertical runs on the lowest frequency, therefore it has the largest capacitors. It's very common as sets age for the vertical to show problems first. The height starts shrinking. May not be able to get a vertical lock anymore. It may be had bad vertical linearity, meaning the image is distorted. So we saw that here where it was only that tall. So that did not surprise me at all. Very happy that the horizontal is doing something. We got high voltage. But we're going to focus on the audio next time. This. So we weren't hearing anything. I would expect to hear some static, some hiss, some hum, some crackle. Well, that seems like a very good place to start because it's self-contained, should be easy to troubleshoot. We feed audio in here, preamp, amp, speaker. You'll be seeing that next time. Thanks for watching.